Good afternoon, good morning, good evening, depending on where you are on this fast forward planet, which is a turbulent place these days on many levels, politically, geopolitically, climatologically, virologically. Is that a word? We're still facing the risk of pandemics just because this one seems to be tamped down. I'm really pleased to reconnect with Gavin Schmidt, who's been a trusted source of mine for, 20 years. Is that right?
Might even be longer. Yes.
Yeah, it could be longer. On climate questions, he's one of the top modelers, and now a top. He's been in a top position at NASA for more than a decade, running the Goddard Institute for Space Studies. That was a longtime domain of Jim Hansen, his predecessor as director. And this year, including this year, 2023 and this year, are so anomalous. There's been so much heat and contention and assertion around the truly extraordinary dynamics of the ocean and atmosphere and ice of the world these days that I thought it would be great to check in with Gavin, and particularly because he just has a piece in Nature. I guess it's commentary. Is worldview like, what is worldview? An op-ed?
I mean, they asked me to write it, so I guess it's a commissioned opinion piece.
Okay. Yeah. Well, let's just get right to it because you're, a busy scientist. And how do you summarize things? When you run into an old friend or something, and they say, "What the hell's going on, Gavin?" Initially, and then we'll get into the questions about what we know and don't know.
Right. Well, I mean, if somebody asked me, the answer is I don't know, and I try in the piece to try and kind of dig down into what is driving my ignorance, and it's not because I'm not aware of the fact that there was a volcano 3 years ago, or that I'm unaware that aerosol emissions are changing, or that I'm unaware that we're starting a new solar cycle, or that I'm unaware that greenhouse gases are rising. I mean, one of the interesting things, you put stuff out there, and like maybe half the comments on it are, yes, well, you haven't thought about this factor thing here, when like they obviously just didn't even read the piece where all these things are laid out.
People are actually predisposed to just have something in their head and think that's
I mean, people seem to have a like their favorite solution for everything, and when anybody says, "Oh, I don't know something," well, it's this thing that I happen to be very fond of. Anyway, so when it comes to temperatures, 2023, it was. It started off as a La Nina year, right? And normally, if you start off with a La Nina year, you expect things to come just a little bit under trend. So we have this long-term trend. We understand that long-term trend. We have been predicting that successfully for more than 4 decades. That bit's done, right? That bit we understand. So we have that long-term trend, and then there are variations around that trend that are associated with shorter period things like El Nino, things like La Nina, things like volcanoes, like the solar cycle. I mean, all of those things can be picked out of the residuals from that trend to see, so that we can get a sense of what else is going on. And so.
Before you go on, is there anything particularly unusual or not well understood about years where you have a flip from a sustained La Nina into an El Nino? Like, that's
happened many times before. Two examples, 2015, 1997, both had very similar transitions, but they did not have the spike in temperatures that we saw in 2023. And so let's go over what actually happened, and then I'll point out why that was surprising, and then maybe think about some of the things that could be to blame for that.
Yeah.
Starting off, we were in a La Nina that should have given in a statistical sense, based on past data, a change of temperature that would have been a little bit below the trend. So the trend is going up, and so a little bit below the trend could still have been a record warm year. I calculated the odds at about 1 in 5 at the beginning of that year. And I made an estimate of what the end of year temperature would be. But starting very early on, by March, we were seeing record-breaking temperatures in the North Atlantic. By April, we're seeing record-breaking temperatures in the global sea surface temperature. By kind of June, we're seeing record low sea ice in Antarctica, on the other side of the planet. It's only really in August and September that the El Nino starts to really come into play. So we'd been predicting that there would be a transition to El Nino from the spring, from around March, quite successfully, and that prediction came true. But the impact of that El Nino really only started to be felt in the late summer, so August, September, and then that built towards the end of the year. But it wasn't a huge event. It was a moderate El Nino event. It wasn't as big as the one in 2016. It wasn't as big as the one in 1998. And so we have that transition, and then we kept breaking those records. Like every month from June onwards was a record-breaking monthly anomaly. And then by the time we get to the end of the year, 2023 is by far the warmest year on record, and in fact broke the record by a record-breaking amount. And this was way outside of the estimated range that I had made and others had made at the beginning of the year, based on the trend and the phase of ENSO at the beginning of the year. And not just a little bit outside the bounds. I mean, like 2 or 3 sigma outside the bounds, and so that's very unusual, right? So what's the basis of that historical estimate? It's the historical data. So nothing in the historical data suggested that 2023 would behave in the way that it did. And we're still breaking the temperatures. We've had a whole year of record-breaking temperatures in the North Atlantic that started in March last year and continues now to February and maybe March as well. So we'll see whether that continues past this. But we have that's a very unusual pattern, right? And it cries out for an explanation, or maybe multiple explanations, and so that's kind of what's intriguing me. And so the basis of the article that I wrote is really, well, how can we quantify these things? What are the different things that could be playing a role here? What might we be not including? What might we be discounting? What might we be not looking at? And so, we've the greenhouse gases have not changed very dramatically beyond what we're expecting them to be. We have the volcano that went off in January 22, right? That's a very unusual volcano, so it put up a lot of water vapor into the stratosphere as well as a little bit of sulfate. The sulfate and the water vapor are now at different levels. They have slightly different properties when it comes to settling out, but the net impact of that seems to be, from the people that have looked at this most clearly, is that should be giving us a slight cooling, because the sulfates are still going to are still, for the time being, winning out over the water vapor. But the numbers are small in either case. Like, we're trying to explain perhaps a 0.2 degrees Celsius excess warming in 2023 beyond what we would have expected, and that gets us, maybe 0.02, so a tenth of the way, right? So that's not big enough.
And by the way, in terms of just dynamics, also something that's Southern Hemisphere, how would that relate to North Atlantic?
Well,
How much is that North
I mean,
Atlantic?
so the water vapor is now that
Oh,
water
it's
vapor
globally
anomaly
dispersed.
has now spread. So
Yeah.
earlier on, it would have just been in the southern hemisphere, but
Okay.
things in the stratosphere they move up and then they kind of spread out on both sides.
Right.
The solar cycle. So we're going into a solar max, which will probably max out in around 2026, perhaps. But again, you know, the numbers that you get from that, the change in the total solar irradiance, the ozone feedbacks, blah 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 blah, you get around another 0.002003 degrees C. Again, not commensurate with the size of what we need to explain.
I mean, you're not even remotely, right? Not even remotely commensurate.
No. I mean, like it would be nice if there was like a whole suite of things, and you know, and there would be some combination of them that added up, and it would be the right thing, and we'd be able to kind of work out what that was. But no, so we haven't got that. People have, some people have said, "Oh, well, it's definitely the El Nino," and this is just a different kind of El Nino. Well, what are the statistics? What element of this El Nino is so different from all the other El Ninos? And I can't find one. This is a moderate El Nino event. It's been like many other moderate El Nino events. It isn't as big as the ones that gave very big perturbations in the past. And so, it's conceivable that things are changing in the way that El Ninos are being kind of teleconnected to the world. And that would be quite disquieting if that was the case. But it's not obvious that anybody has demonstrated that. So that's in the realm of possibility. Yeah. Okay, and then there's other kinds of human forcings, right? So people have highlighted the change in aerosols more generally. So aerosols in the atmosphere, pollutants, nitrates, sulfates, black carbon, things in general have been going down because of Clean Air Acts and the like. And there was a very specific shift that happened in January 21, which was that the shipping fuel was mandated to have 80% less sulfur content, and so 80% less sulfur dioxide emissions, and that doesn't quite translate to 80% less sulfate, but one imagines less aerosols from that in these marine shipping lanes, and that's quite a big deal, but the evidence that this is going to cause a huge change in global mean temperatures is scant. We've done some analyses of this. There's an ongoing comparison of all the different models and they come up with a range of numbers, but they don't seem commensurate with the size of the change either. In our model, again, it's on the order of hundredths of a degree. Yeah. So. So it could be that we're doing that wrong. Could be that other things are going on. Could be that other aerosols are going down faster than we anticipate. Yeah, that's also possible. We're waiting on updates to the aerosol emissions from the community that puts those together, and we're waiting for these. Pretty much like they should be here this week or next week. But we've been saying that for a few months now. But right. But they should be around soon. So and then we'll be able to have a look. The Antarctic issue is very odd and doesn't fit into any of those paradigms. So, is that just a blip that just happens to be coincident with this? Is the North Atlantic a blip that happens to be coincident with this, or are these things connected in some ways? So it's very unclear at this point.
One other thing I want to ask you before we get to the part of the paper, your article that's about what to do, and you do talk about data and some new sources of data. I wanted to also ask about just rarity. Are there other years that, when you look back historically, that not necessarily are replicating what we're seeing right now, but that have a deep anomaly that has not been explained. You know, I wrote a book about the history of climate and stuff, and there are some years where it's really clear, but then there was a period. There are periods where there's things that have happened on the Earth that don't have, like a volcano or something. So could this just be a really weird moment on a heating planet?
Well, yes. I mean, but weird moments don't happen without actual processes. Like where
Right.
did the energy come from and go to? So
yeah, I think it was, you know, there's some people out there who like to point to the 1870s as being one of those moments you wouldn't have wanted to live then, that kind of thing. So I just yeah. So walk me through. So you said there are ways to understand what would be driving even that kind of year, right?
Oh, right. I mean, the energy budget is pretty clear, right? You know, you have energy coming in from the sun, you have energy reflected from the clouds, you have energy that's trapped by greenhouse gases and water vapor and clouds. And so, you know, you can do a budget, and we will be able to do a budget once we have models that are able to replicate what's been going on. And we will hopefully be able to do a retrospective on 2023 in the same way that these folks did it for the 1870s.
With a lot more data.
With a lot more data, right? So we'll have ocean heat content data. We have top of the atmosphere radiative fluxes. You know, these are things that we don't have for anything prior to the 1970s. So you know, it should be easier, right?
Yeah.
It should be more obvious. But people that are pointing to, oh well, you know, the heat imbalance was greater. I mean, it's basically just saying, well, it got hotter because it's heating, and like
Right.
that's no explanation at all. Why did it do that? That's the key. Is it aerosols? Is it clouds? Is it pattern effects? Is it internal variations? You know, there's a lot of stuff that could be at play there.
Yeah. So by the way, Zeke Hausfather is in the studio, and I thought he could pop in just briefly to if he had a question or a comment too. Is that okay?
Oh, for sure.
Yeah, and I haven't talked to him since, I don't know, God, the last time was driving around San Francisco somewhere. So it was ancient history. Hey, Zeke.
Hey, Andy. Good to see you, Gavin.
Yeah. So this is wonderful. And Zeke, I know you had done some tweeting and some analysis recently about that this isn't as anomalous as it feels like or seems like. Could you talk about that?
So I'm going to be a bit boring here and tell you that Gavin and I are sort of in violent disagreement, or violent agreement, I should say, on this point. I published a piece over at Carbon Brief back in January, sort of making the same point that like 2023 was very unexpectedly warm compared to what we anticipated. And so, you know, Gavin publishes an estimate a year ahead. The UK Met Office also does. I publish one. Robert Rohde at Berkeley Earth publishes one. We all missed 2023 by a very big margin.
Yeah.
My point,
and it's worth pointing out that we've been doing this. I don't know who was the first. I may have been the first to start doing this, but since at least 2015, and we have never missed.
Wow. And if you look back at sort of a hindcast of our respective approaches, like you don't really get misses as big as we saw this year, except for like Pinatubo erupting or similar types of weird external forcings. So when I published that graph about, you know, where observations are with respect to climate models, the point was more or less that we're not outside of the range of warming overall with what climate models expect. Like we expect to see an occasional year around 1.5 degrees relative to pre-industrial today. And 2024, I think we'd all agree, is when we naively expected that to happen. I think what's really weird is why it happened in 2023. In fact, if you look at monthly temperatures recently, like, yes, we're setting new records every month now, but by a margin that's a lot more understandable. Like January, February, and now March seem to be in the somewhere like 0.1, 0.15 C above the previous record for that month, which is broadly what we'd expect after a big El Nino peaks. It was last summer and fall when we were setting records by half a degree C that it was really bizarre. And, you know, we will eventually, hopefully, figure out why that happened. But when we see weird stuff like this, it's both exciting from a scientific standpoint and a little disconcerting because, you know, for something as big and complex as the climate, it's not good to have things happening that we don't have a good explanation for.
Exactly.
Yes, yeah. So Gavin, take me a little bit more there, because your piece that you wrote in Nature has a concerning kind of coda. You know,
Well,
so,
yes. I mean, we don't want to be surprised, right? I mean, sure, it's scientifically interesting, and and it gets our kind of academic juices flowing when something like this happens and we're rushing to explain it. But this is a system that has absolutely huge ramifications for people all around the world, and for extreme weather, and for all of the sea level and all the rest of it. That has real implications, right? So if we do not understand what is governing, these record-breaking temperatures, then that puts a question mark on how credible the predictions are for the future. Now, Zeke and I worked on a paper a few years ago, looking at how well we have actually predicted things over time, and we've done really quite well, even from like the toy models that people were using in the 1970s to the first transient GCMs to CMIP3, which continues to be incredibly accurate for some unknown reason. And even the models that we've only just finished with, the CMIP6 models. Now we've also worked on assessments of those, and there are some that you want to throw out for this kind of calculation because they have a too high climate sensitivity. But even if you take that out, our ability to predict those long-term trends has up until now been very good. And 2023 doesn't really change that. The issue that we're seeing with 2023 is exactly why specifically 2023 was so warm. Not is it distinguishable from things that happened in the ensemble, but it is in fact distinguishable from what happened in the ensemble, because there isn't a single run that shows these kinds of temperature records being set in August and September and October and November in a year prior to an El Nino event. Not a single one out of hundreds.
Wow. One thing that will be interesting to look at is what happens for the remainder of 2024. Like if 2024 goes back to being a normal El Nino year, if it becomes analogous to 2016, temperatures fall later in the year, right, it'll look more likely that whatever happened in 2023 was probably driven more by variability than some sort of external forcing. Like if it's sulfur causing it, for example, because the air bars are really big in aerosols, some of the estimates are big, I'll acknowledge that. If it was sulfur causing it, we'd expect that to persist and even grow over time as the oceans respond.
Right.
Whereas, if we stop setting records by very large amounts later this year and fall back to, more similar temperatures to what we saw in previous years.
Yes.
Yeah, it'll tell us something. It won't give us the answer of what caused it, but it'll hopefully give us a little bit of encouragement that it might not be a new normal, so to speak.
Well, I mean, it's a new normal while climbing a massive hill as well. So.
Yes, we're still going up.
Right.
So a lot of this discussion, doesn't really implicate those long-term trends. But if this isn't a blip and it's something systematic, then that's something that we need to be including, and that's something that we need to understand. And if it's a blip, right, then but it's still outside of everything that we've predicted, that means that we need to be expanding our range of what we think internal variability can do beyond that we've been thinking about so far. So I think that there are implications regardless of what happens to the explanation, unless if you think back to the hiatus, going back to 2013, 2014, a lot of the resolution of that issue was that the data sets themselves, the observational data sets, ended up being, it turns out that they were biased, and when they were revised, the whole situation kind of disappeared, and so it became much less interesting, except for the people making the databases. I don't think that that's going to happen here. We have evidence for the exceptional warmth, the anomalously exceptional warmth in 2023. We see it in the MSU records. We see it in the AIRS records. We see it in the surface temperature analyses. We see it in the reanalyses. It's almost certainly definitely there. So that isn't going to disappear with predictions of the observational data.
So I had sent this around, this post around by email to a bunch of people earlier in the day, and Tim Palmer at Oxford replied, and he basically said it's model insufficiency. He's at least this only addresses. He thinks if you had better, bigger, better models and everyone working together, he says here, if we do not want to continue to be surprised by climate change, we need to invest considerably more into climate modeling. We need centers of dedicated exascale computing, sort of a CERN. He's made this point about CERN.
With all, I mean, I enjoy talking to Tim, and I have had this conversation with him many times. But I mean, his answer for any mystery is always the same. We have to invest in higher resolution.
He's not alone in that.
No, but the problem is that there comes at a cost, right? So to have a model of the resolution that he is talking about, kilometer scale climate modeling, not weather modeling, climate modeling, right, is a factor of about 10 to 100,000 increase in compute.
Wow.
Right. So sure, if we had that collectively, then that might be something that we would want to do, at least, at least experimentally. But those resources do not exist. And you might say, okay, well, with a little bit of machine learning will get you maybe one order of magnitude.
Right.
But you still need 10,000 times more compute. And in doing that, I lose the opportunity to do 10,000 times more other things, like exploring the uncertainties in the aerosols, exploring the uncertainty in climate sensitivity, exploring the internal variability of large ensembles. And we have learned, I think, as a community, that we cannot ignore those things. We cannot ignore internal variability. We need to be sampling that. We cannot ignore the uncertainties in the forcing fields, particularly the aerosols, right? We have to be able to explore the range of structural variations in the models. If we have one model and it ends up like the DOE model that was supposed to be the high resolution model that everybody and it comes up with a climate sensitivity of 7 degrees for a doubling of CO2, then it's useless, frankly.
Yeah.
Right? That's not exploring the uncertainty. That's just giving us the wrong answer.
Yeah, there are a couple of questions that have come in. One of them, Jeff Sukan asks, will the climate models from now on include a larger margin of error because of this? Does this anomaly change the shape of the uncertainty?
So the uncertainties in different kinds of projections come from different sources, right? So the uncertainties in the model projections for the long term come from the internal variability that those models themselves generate. So none of what's happening now is going to change that. So those projections are going to stay exactly the same as they are. Now, is it the case that my statistical predictions for climate 1 year ahead, is that going to, are those uncertainties going to expand? That the answer is obviously yes, because it's a statistical fit to past data. So this last year, in fact, I just did that test this morning. That last year expands the error bars. But in fact, it still doesn't include last year because last year was so anomalous. So in some of those things, yes, the ones that are based on observed data, that there will be an expansion of the uncertainties because the real world has told us that we need to include something else.
Yeah,
now,
sorry.
Yeah, come on.
There's another question that I'll lump into the. Could could we be seeing a tipping point? Gavin, you and I go way back on tipping point. This is a sort of a biological one here, but you know, a lot of people have been playing this as, oh my God, we really are now on the cusp of doom. And how do you, maybe each of you could talk about how you kind of.
I mean, but you know, tipping points are not magic, right? They're not things that happen with no trace. Right? So if there's a change in phytoplankton that's changed the albedo of the surface of the ocean, we will see it in ocean color measurements. You know, if there's a change in the emitted aerosols of DMS, we will see it in the aerosol of Twitter, and we will even see it maybe as sulfate directly with the new data that's going to come from the PACE satellite. Which will start producing data in about 4 or 5 weeks.
That's great.
So, you know, I mean, these are testable hypotheses, right? You know, people are saying, okay, well, maybe this has changed. We can mostly measure those things, and so it isn't. You know, it's not a black box where something mysterious is happening and then temperature is the output. You know. All of these processes, the clouds, the radiation, the reflectance, all of these things are measurable and quantifiable.
Zeke, any thoughts on that?
Yeah, to add to that a little bit, there's a big review paper on tipping points that I was an author on with Richard Betts and Stephen Sieberwing and a bunch of other people. It came out in 2022. And in it, one point we made is that the popular conception of tipping points as sudden climate cliffs that we sort of walk over one day is very different from the way we discuss tipping points or tipping elements in the climate literature. You know, they're much more slopes that are a lot harder to climb back up than they are everything's fine and suddenly you fall off a cliff. There's actually a great term for the latter type of tipping point in a Bob Cobb paper, which is Gladwellian tipping points after Malcolm Gladwell. We don't actually use that term for obvious reasons because it's confusing. But so, you know, yes, there are going to be a lot of changes as the Earth warms, and there are a lot of tipping elements like, you know, thawing permafrost, like changes in the Earth's carbon cycle in various ways, loss of forest lands, fires, and boreal forests that we're already starting to see. And there's other processes that can moderate those in some ways. You know, as boreal forests burn, we also see more vegetation growing at higher latitudes, which is a corresponding carbon sink. And so how all of this ends up panning out to the Earth system is complicated. It's the reason we have Earth system models. They're not perfect. They don't include everything yet, but they include more stuff every year. I'd also note on this broader question of where we're headed, like 2023 is a really extreme year. And it's not by any means outside of the bounds of where our long-term models thought things would be today. If anything, the last decade or two has been a little bit below where the latest generation of models thought, which is one of the reasons Gavin and I had a paper recently on why we think that they might be running a little bit too hot in aggregate. There's been some people arguing to revisit that in light of last year. I think that's premature, but we'll probably argue over that over the next decade. But the point is, there's not evidence that it's necessarily worse than we thought, but there is evidence that some weird stuff is going on that we need to figure out an explanation for. And
Gavin, your I keep wanting to call it a paper. Your commentary gets at some of those things too. Do you feel overall you have the observational inputs you need to enrich the blend of things you look at to try to clarify these questions, or is there something that's been missing for a long time that's not just exascale computing, but that could really help with some?
Well, I mean, so composition of aerosols has been missing for a long time. You know, we NASA and folks that I work with at NASA have been trying to get a polarimeter into space to measure the composition of aerosols for decades, and we almost managed with the Glory satellite, but unfortunately there was a fairing issue with the second stage, and it ended up in the South Pacific instead of in low Earth orbit, which was pretty tragic. And now it's taken us 10 years to get another instrument into space that would do the same thing. So that's 10 lost years, effectively, in terms of our ability to be precise about what the aerosols are doing, how they're doing it, and how they're interacting with clouds, and what the effects are. So we anticipate that the PACE satellite will give us a baseline that we can then train the models to. And I think that once we do that, the models will be better constrained. And then when we go back and revisit what's been happening over recent years, we will get a narrower uncertainty. We will get a more definitive answer. And so we're waiting on that. We're also waiting on updates of emission fields. So right now, the official emission fields that we have only go up to the end of 2019. We are anticipating an update to that at least to the end of 2022 imminently, and to the end of 2023, hopefully by the end of the year. And so when those data come in, again, we will go back, we will revisit, we will be able to do a post hoc reanalysis of what's going on, and our opinions collectively might change about what was important. But right now, there's not been any published data that suggests that anybody has, an answer that's commensurate with the size of the anomaly. Now, there might be stuff that people are working on that I haven't seen, but I haven't seen it. So, as that comes out, we will be revisiting that. But I'm perhaps a little unusual here in that I'm not banging the drum for any particular thing. I'm genuinely puzzled, and I'm open to any of these things being the cause if we can demonstrate it quantitatively.
Right. Well, this has been a great dig into this commentary that you just put out. I also have I invited Adam Sobel to come on, because he has a commentary, a worldview thing, the same, I guess it was a day before yours, on Doom, and you guys are happy. I'd be happy to have you pop off or to stay on. This is unintentionally an all-male panel. That does happen sometimes, but I'm going to show his commentary too. And Gavin, it's been great to have you on. So feel free to stay on. But that was a really valuable discussion. And same, Zeke. If you can hang out if you want, or not. Let me share my screen. I'm having a problem here with getting the right screen. Oh, here we go. So here they are side by side. Are we doomed? Climate models can't explain huge heat anomaly. So we're going to talk about what to do about these feelings and the like. And Adam, it's been a long time since I've been in a conversation with you. For those who don't know, Adam had worked a lot on the basic physics of the climate system, and then wrote a paper that excited my interest because it was about his shift to taking a problem-solving approach, applying his science to society's challenges, especially what's called adaptation or resilience building. So, Adam, I don't know if your microphone is on. Yeah, you should be able to say hi.
Hi. Yeah, I'm sorry to have missed the first part of the conversation.
I'm sure you still care a lot about climate models.
I would have liked to hear about what these guys had to say about the crazy anomalies, but
you can review it after the fact. So we're going to talk about how to cope with the daunting uncertainties. And we were talking about the uncertainties. We started this conversation, Gavin, when I said, well, one thing I asked Gavin right off the bat was, if you run into a neighbor or someone in the market, they say, what the hell's going on? And Gavin's response was, well, we don't know. But at the same time, we know a lot of things that need to be done to mitigate climate risk. So Adam, maybe you could dive in on what drove you to write this.
Right. What drove me to write this? I mean, well, the Nature Editor asked me to write something, but why I chose to write this, it's not a response to any particular thing that happened. It's not a response to the current SST anomalies. It's a response, I guess, to two things. I mean, how I framed it was, people often ask me this question, and I think most of us, if we're in this business, we've been asked this. I'm sure Gavin and Zeke have been asked this by people. And I've been asked it in two contexts. One is just, random people that you may know, or you go give a public talk somewhere and people ask you, like, how bad is it really? You get that. I've also got it in a more professional context sometimes. As you mentioned, Andy, I've been, I still work on the basic physics of weather and climate, but as you said, I've been doing some stuff that's a little more applied, a little closer to adaptation, and interact with people as part of that in the insurance and financial industries. And there, I guess one thing is that any kind of stakeholder that we work with people in NGOs and stuff too, any kind of stakeholder, when you talk to them for a while and they're coming to us for some kind of data or modeling or something, and I've started to feel that if you're in those conversations for any length of time, I've started to feel that it's almost more important to talk about the things we don't know than the things we do know. Sometimes people are paying us to do something and then we give them what we've done, but a lot of times I feel like the tension is that in research science, if you're writing papers for your peers, which is what we do most of the time as scientists in academia or government, your job is to advance knowledge, and you advance it in any direction you can. And sometimes the really hard problems you can't solve, so you don't, right? You pick off some piece that you can solve and you write a paper, and that's fine. But if you're dealing with somebody that has to make a decision, that has to understand the big picture, it's a different question. Like, you can't just say the things you know. Sometimes the things you don't know are a bigger deal. And I think people who are asking for a sort of holistic assessment of how bad is it, that's what they're asking. And so I guess I wanted to get at two different things. And by the way, I didn't choose these images or anything, or the headline or anything like that, as is typically the case with these things. I wanted to get at two different aspects of this. One is just what some of the uncertainties are that I don't want to say we don't talk about them. I think as scientists, we do talk about them, but sometimes they're not the ones we're writing as many papers about because they're things that are hard to solve. And the example that's first and foremost in my mind right now is the tropical Pacific. We've been talking about the El Nino and La Nina events, and the climate models all predict that we should be having a more El Nino type climate as we get warmer, and the observations have done the opposite, and we still haven't sorted out, whether the models are wrong or whether it's just, a fluke or what. But that's a big, very consequential question for present climate risk assessment as well as future projections. And so that's an example of something where I think we just can't answer it yet. We can't look at the spectrum of models. Almost none of the spectrum of models that's out there now looks like recent history. And so, that's a big uncertainty. So there's one thing I just wanted to write about was just some of those big uncertainties. But the other thing was that I think when people ask, how doomed are we? I think some people, they ask us as scientists thinking that we can really answer it. And I just wanted to communicate that we just can't, because it isn't a science question, and on some level, this is totally obvious. And on another level, I don't think it is to everyone, that what does it mean to be doomed? Does it mean we're all going to die next year? Like, some people think it means that. Like, no, it doesn't. We're not going to. Okay. That's not going to happen. Is the human race going to be extinct in a decade? Like, probably not, unless we all shoot nuclear weapons at each other or something. But it's to say that this is really a question about concrete things, like how far in the future are you thinking about, how bad an outcome does it have to be for you to call it doom. But it also depends on our perspective, who we are and where we live in the world, and it also, there's a lot of, and also I wanted to, I guess, take issue is too strong a word, but sort of counter what I think you sometimes see creeping up in our field, which is a little bit of climate determinism, where we act as though the whole future is about climate. But my own feeling living through the last, years in the United States and in the world is that, like, a lot of big scary things can happen that aren't climate, and that in the short term sort of eclipse climate from our view. And maybe they should, maybe they shouldn't, but it's just to say the future is more complicated than climate. So I was trying to wrap in a lot of things and write a sort of personal piece that was informed by science, but was trying to put science sort of in its place in thinking about the future, which is as human beings, we never really know what the future holds for ourselves and as a society. And there's a lot of other things we can't predict. I mean, I guess the other point I wanted to make was, as climate scientists, we talk about the uncertainties and how challenging they are, but the uncertainties and everything else are worse, right? I mean, ask people who are trying to predict like interest rates. Like, what do you think the interest rate's going to be in 20 years? Or let alone like what wars are going to happen and who's going to, there's just what science technology are going to evolve to be. Think about AI and how rapid the changes are. Who thinks that? Lots of people are worrying about that, but who really knows what life is going to look like? So I was just trying to. I think sometimes we make these climate predictions, we look at them into the future, and we focus so much on that we forget all that context.
Yeah,
so I was just trying to say a lot of things that are obvious, but on the other hand, I think they get lost. So that's all. It was just a personal view of all of that.
I'm glad I saw it. Someone else had tweeted or something or X'd it, whatever you say now.
Well, I tweeted it, but maybe somebody else.
There are two thoughts that emerged for me. One is, and I'm sure both Zeke and Gavin might have thoughts about this. One is when you get asked questions that aren't a science question, and one is when you talk about uncertainty that is maybe not reducible. I've written before about what I've called, like, the IPCC has all this metrics for very likely, but they're only toward knowledge. I've never seen the IPCC say it's very likely we won't be able to reduce the uncertainty around, let's say, sea level rise by 2075. It's very likely we won't be able to answer that question for you any better, in AR7 or 8 than we did in AR6. And so that's one thing. But the other thing is that the preceding question is about the importance of saying I can't answer. That's not a science question. Like 1.5, Gavin, you've written about 2 degrees. When 2 degrees was the threshold long ago in real climate, you got into that issue of these certain things are not about the science. So do you guys want to weigh in at all, or?
Well, I mean, there's a reason why IPCC doesn't say that we'll never know any better, because eventually we will know, right? So even if we have to wait till 2070, we will know what the sea level rise is in 2070. I mean,
you mean just for time passing? Yeah.
I mean, they are reducible because eventually we'll get there, and the estimates of future change are going to be better the closer you get to it. I mean, it just stands to. That's just, it just seems clear. And so, some things that have come up recently may be irreducible. So, exactly what the baseline temperatures were in 1850, it may be that is irreducible. There just isn't sufficient data to be able to constrain that better to, 0.1 or maybe 0.2 degrees Celsius, right? Which is a little bit awkward for the political process, because they pinned something to temperatures in 1850 without really thinking about whether that was a sensible thing to do. Anyway. But so there may be irreducible uncertainty there. There may be irreducible uncertainty in climate sensitivity, but I think it can still be reduced from where it is now. Yeah. There's irreducible uncertainty in 2-week weather forecasts. But is it reducible from what the forecasts are doing now? Well, yes, it is reducible, but perhaps not by very much. We have we have 40, 50 years of experience here in reducing uncertainties, right? So I think it's real. It's not surprising that we think, based on that working hypothesis, that we can do this, that we will in fact do this.
Okay. I mean, as far as uncertainties go, when it comes to climate change, they're decidedly not our friend. The late Marty Weitzman had a great saying that when it comes to climate change, the sting is in the tail, which is a very nerdy saying because it refers to the tail of the PDF distribution. And so in many ways, we should be designing climate policy not for the most likely outcome, but for the 10th percentile outcome, or at least the 33rd percentile outcome. What does it look like if we end up in the bad side of this range. At the same time, part of me wonders how much those uncertainties practically matter to what's being done today. Say we discovered the climate sensitivity was 4C for doubling CO2 instead of 3C. We've already told the world's countries to meet that if they want to meet their stated goal of limiting warming to 1.5 degrees, they have to cut global emissions in half by 2030. We're not going to do that, but we discover this new finding that climate sensitivity is higher. Now we say you have to cut your emissions 66% by 2030. Neither of those are going to happen. So I'm not sure the reality on the ground in terms of what we need to do to solve this problem fundamentally changes as we reduce these uncertainties. And at the same time, reducing them is really important for other reasons, right? Adaptation planning, for understanding what's going to happen, maybe to help convince people to take action, though I feel like what we've already discovered is if it hasn't convinced them already, then I'm not sure what it's going to take. So yeah, I sort of have mixed feelings on the value of uncertainty here.
Yeah, I agree with everything these guys are saying, but I want to add on one thought. So this, I didn't write about this so much in this particular piece, but it's sort of a subtext of it, which is the difference between thinking about adaptation and mitigation. So I think, the IPCC brought up the IPCC, and the IPCC does many things, but fundamentally my understanding of it is it exists to inform the governments negotiating about emissions reductions. And so that's the orientation of it. So the IPCC is, and climate science, I would argue, most mainstream climate science, to the extent that it's been thought of as policy relevant, has been mostly around, making the case for decarbonizing the economy, which is totally appropriate and what we have to do. And, no, I don't think any of us would disagree about that. And I agree with what Zeke said, that in the near term, those uncertainties are not that relevant for that, because we already need to know more than we're doing. The reason we're not doing it is not science, is not uncertainty. So, So that's all true. What I think, but I do think adaptation is different, and we're maybe a little less accustomed to thinking about it. And I guess I would make 2 points about it. One is that there are some adaptation decisions that people want to make immediately. I mean, in the very short term. And so for that, whether we can reduce the uncertainties by doing more scientific research is kind of irrelevant, because we have to do the thing now. So the most useful thing we as scientists can do is characterize the state of knowledge, whatever the uncertainty is, whatever we know, whatever we don't know, to tell people, and everybody has to make their own decision as best they can with that. And I think that does, I wouldn't say we're not doing that now, but I do think it gives there's a little bit different type of research you do when you're trying to narrow the uncertainty versus when you're trying to characterize it as fully as possible in a decision relevant way. I think those are two somewhat different things. And I think the latter kind of research is done in some parts of the field, but it isn't done as much as I think we could, now that there's more adaptation happening and demand for it is increasing. So that's one thing. The other thing I think is that one of the reasons I wanted to write about doom is that I think, I actually had there was one paper that came out, I don't remember which paper it was, but it was one of these papers that said, like, the thermohaline circulation, might shut down tomorrow, kind of thing. And I was contacted by some people actually at an investment firm, a real company that decides how to invest money, that wanted to know about this paper. And I was like, what decision are they going to make on this paper? It was sort of like they just wanted a scientist to tell them, like, are we all going to die next year or something? Because if so, maybe we don't, maybe that changes how they think about investing their money. And it was one of these things where you literally talking people down for a minute and saying, I don't want to say it's not bad. I mean, this is a thing that could happen. This paper is not junk. It wasn't a terrible paper. It was just, you have to read it in context and know that, it was one model, and people, you can't say how quickly, there's a lot of things you have to do to qualify. We as scientists know how to interpret these things, and we don't overreact, but sometimes the media, pitches them in a very extreme way that makes people think, I think, in other words, I think excessively doomy ways of reading the science, which are often just misinformed ways of reading the science. Not to say that we should, when it comes to mitigation policy, we should act like we're close to doom, because in the long term, like we might be, and we can do things now that can avoid it. But if you're thinking about things to do today, like, I think that kind of thinking almost stops you from doing constructive things you can do, because you think maybe we're all going to die anyway. So I just wanted to say that I think it's useful. I think we as scientists could spend a little more time thinking about the different ways our science is used and how you might do and express the science differently depending on those uses. So I'll stop there. I know Gavin wants to.
Let me add one more thing to what you said, right? So you made the point, I think, quite cogently that what prevents us from mitigating more is not more science, right? Like more science is really kind of irrelevant at that point. But what prevents us from doing better adaptation and climate resilience is also not more science, right? Almost all of these decisions are being made with people not taking climate change into account at all, because they don't know how to access the information that we already have, even with the caveats, even with the uncertainties, right? Many investment decisions are being made without any input from future projections and climate change, even for silly things like not silly, but obvious things like coastal construction. Yeah. People are not building in to these decisions the information that we already have now, regardless of how how caveated that is, and that is something that again is not going to be fixed by more physical science, right? It has to be fixed by education, by databases, by co-production, by scaling, by there are lots of other things that we could do to improve the take-up of the knowledge that we have right now for the decisions that we are making right now. And there's still a huge gap between what we in this room know, caveated appropriately, and what people are using to make decisions. And that's a gap that really we have to really work hard to fill. And I'm a representative of the federal government here. It's something that the federal government should be doing and supporting much more than it is right now.
Yeah. Well, I think I just want to respond to that. I think I agree 70%, Gavin, but I guess I would make the argument. I have made the argument. Andy referred to the paper that I think that if we're talking about the value of new science for decisions, I would argue there is a little more sort of marginal value in adaptation than mitigation, because although you're right that there's a lot of decisions being made without taking climate into account, in some of those cases, I think the climate data that exists is not optimally, wasn't really designed to do that and could be. So it may not be the most fundamental climate knowledge in all cases, but downscaling and uncertainty quantification and bias correct, all the things that make it really decision relevant. I think we're not so good at doing that. The private sector has raced ahead, and I would argue we in academia and government are a bit behind on that. For example, it's not that there aren't people doing it, but there isn't the kind of community like assessment and synthesis behind like usable climate data. And I know this from personal experience. It's not just in the private sector, but even people in federal agencies like FEMA and state and local governments that are thinking about adaptation. They are told they should take climate into account, and then they go, okay, what data do we use? Should we get the climate models off the archive? And we tell them, oh my God, no, you can't do that. You don't know what you're doing. Like, it'll be a disaster. And they say, okay, what should we use? And we're like, well, there's some web page that a guy made where he downscaled some stuff. And it's like, there isn't really we haven't responded to that challenge, I think, coherently as a field. So I think the extent to which, more science would help, I would just argue is a little greater in adaptation than mitigation at the present time, not necessarily in principle, but at the present moment, even though the science might not look like what we've necessarily all been doing, but some kind of science.
Yeah, I will defend.
I don't know that that's really science. I mean, it's information distribution.
Well, I think it's more than information distribution. I think there's real science in the layer between current climate science at the degree that we have consensus around it from IPCC and CMIP and all those things, and what the user wants, and done optimally. I think there's real science in the layer between there. We may treat it like it's not, but I think we're shortchanging it.
I'll just say briefly, I think Zeke wanted to say something too, but obviously the social sciences can play an enormous role in shaping those interfaces, or at least testing what works and what doesn't work. I've done a bunch of shows on here with visualizations, and by the way, mostly no one knows what works. Kind of like Gavin talking about what we don't know about this stuff. But even the warming stripes, Ed Hawkins' warming stripes, they look really cool. They're on the cover of The Economist, they're on buses and stuff, but no one knows if they work. So So these are, oh, there we go. And actually, there was a colleague at Columbia. What's his name? Who lives in Piermont, or not Piermont, where he said they use the red to blue stripes on their website for their town climate committee, and everyone thought it was political red and blue. I mean, that's a classic case of we think this is really cool, but guess what? It gets misperceived. So the social sciences play a huge role. And Zeke, and then I have to wrap up soon, just because you're all too generous with your time. And there's a really good audience, though. So Zeke, thank you again.
I was just going to make a quick plug that, I agree that there's a lot that needs to be done on making downscaled climate model data more useful. It's often misused, and often the users don't understand its limitations. At the same time, I would make a plug that the recent National Climate Assessment did a pretty good job of both creating new downscaled data through LOCA2 and a few other approaches, and putting together an interactive atlas that everyone can use to download local climate information for their location for help with things like adaptation planning. So at least if they're in the US, check out the 5th National Climate Assessment and its climate atlas.
Thanks, good point.
Gavin, any last thought from you before we call it a day? Oh, you're muted. Gavin, you're muted. You were muted.
I said what I had to say.
Okay. Hey, this is really good. I'd like to do some of these open jams maybe a little more. This was a pop-up opportunity, drawing on Gavin's valuable paper on what's happening and what's understood and not understood about the extremes in the climate system at the moment, and Adam Sobel on the extremes of doom that are sometimes surround us in both the communication and practice of the science and solutions. And Zeke Hausfather, someday, Zeke, I'll get your name trippingly off my tongue, at Stripe, and part of the National Climate Assessment and more. So thank you all for being part of this today. Anyone who's watching this gets archived immediately on Facebook, YouTube, LinkedIn, Twitter, and even Twitch, even though I don't have a clue what that means. And I'm always here for future conversations. The scrolling bar at the bottom tells people how to get in touch. And I can forward questions to our guests. Thank you again, everyone, for jumping in.
Thanks, Andy.
Thanks for hosting.
Let's see what happens in the coming months.
Yeah, it'll be an exciting year.
August, I guess, is an important transition point. Maybe.
We'll see.
We'll see. Thanks again.
Okay, bye, guys.
Hey.